Hey everyone, I'm Jordan and me.
I'm Quinn, and today we are talking about something that connects the Manuka honey directly to the hospital.
Yeah, and as a large-scale commercial beekeeper up in North Dakota, I have to admit I came into this with a pretty healthy dose of skepticism.
Oh, I'm sure. I mean, the market is flooded with claims.
Exactly. When you are out there running thousands of colonies, prepping pollen sub, checking on foragers in the yards, or, managing queen breeding lines, you get to know the commercial honey supply chain inside and out. You
Right.
know, the processing, the grading, and frankly, you learn to spot the marketing fluff pretty quickly. Manuka honey commands this absolutely massive premium on the market, and for a long time, I just wanted to know if that price tag was just hype.
Which is a totally fair question to ask.
Right. But today, we're going to unpack the hardcore clinical science behind why this specific honey is being used in modern medicine to treat wounds that nothing else can fix.
It is such a fascinating bridge between two worlds. My background is actually in apiology, which is the specific study of honeybees and melitology, the broader study of all bees. But I also spend a massive amount of my time working in wound microbiology.
Which is just a wild combination of specialties.
It is, but I essentially live right on that bridge between the hive and the hospital. Today, we are going to look closely at the exact mechanisms, the how and the why, behind bee behavior, honey chemistry, and how those factors translate into a clinical treatment that actually destroys bacterial fortresses that our modern antibiotics cannot even scratch.
And to make sure you, the listener, can follow along with the exact medical science we're looking at, you should pull up the full research page. It's called How Manuka Honey Destroys Biofilms over at Manuka and Wound Science.
Highly recommend having that open.
Yeah. You can find all of this by going to manukawoundscience.org. I will spell that out slowly so you can get there. That is manukawoundscience.org. Everything we discussed today, from the chemical breakdowns to the clinical protocols, is sitting right there.
Our mission today is straightforward, but incredibly complex when you actually look under the microscope. We want you to understand exactly how this specific medical-grade honey breaks down the defensive structures of chronic infections.
The structures that cause all the problems.
Exactly. To do that, we first need to understand the stakes. We are talking about chronic wounds here. Diabetic foot ulcers, severe burns, surgical sites that simply refuse to close for months or even years.
Wow, years.
Yes. And the reason they don't heal comes down to something called the biofilm problem.
Right, the biofilm. I hear that term thrown around a lot in agricultural and medical spaces. For everyone listening right now who might be picturing just, I don't know, a puddle of loose bacteria in a wound, can you explain what a biofilm actually is and why it makes an infection so stubborn?
That puddle of loose bacteria is actually the biggest misconception out there. Bacteria in a freshly infected wound might start out as free-floating single cells. We call those planktonic cells.
Planktonic, like plankton in the ocean.
Spot on, just floating around on their own. But in a chronic wound, that is rarely the case. They don't stay solitary. The bacteria actually collaborate to build a highly organized, protective, three-dimensional fortress. The walls of this fortress are made of something called the EPS matrix.
EPS matrix. Let's make sure we translate that for everyone. What exactly is this fortress made of? Is it a shell?
EPS stands for extracellular polymeric substance. Think of it less like a hard shell and more like a dense microscopic scaffold or a really thick, sticky web.
Okay, a sticky web.
It is constructed out of polysaccharides, which are complex sugars along with proteins and even extracellular DNA that the bacteria deliberately secrete. They use this sticky matrix to glue themselves firmly to the wound bed and to shield the entire bacterial colony from outside threats. That includes your body's own immune cells and prescription antibiotics.
So it's not just a clump of cells. It is a fortified, microscopic city. And if I'm reading this right, the clinical data highlights that once they are safely inside this EPS matrix, bacteria become up to 1,000 times more resistant to antibiotics than they would be if they were just floating around planktonic.
Yes, up to 1,000 times.
1,000 times. How is that magnitude of resistance even physically possible?
It really comes down to three incredibly effective layers of defense that the EPS matrix provides. First, you have a physical barrier. The matrix itself is so incredibly dense and thick that it physically blocks large antibiotic molecules from getting inside.
So they just get stuck.
They literally cannot diffuse through the scaffold to reach the bacteria at therapeutic levels. They just bounce off the outer walls.
Okay, so layer one is a massive physical wall. What is the second defense?
The second is chemical inactivation. This fortress isn't just a passive brick wall, it is actively armed. The biofilm matrix contains specialized enzymes floating throughout the gel. For example, some bacteria produce beta-lactamases.
Beta-lactam.
Right, those are enzymes specifically designed to seek out and destroy penicillin-class antibiotics on contact. Before the drug even reaches the bacterial cell membrane, it gets neutralized by the fortress itself.
That is wild. It's like having a moat filled with something that dissolves any weapon thrown at it before it even hits the castle walls. And the third defense.
The third one is perhaps the most frustrating for doctors. It's metabolic dormancy. Deep inside this 3D matrix, oxygen and nutrients are incredibly scarce. So the bacteria adapt by going to sleep.
They just shut down.
Think of it like a bear hibernating through a harsh winter to survive. They enter a dormant, slow-growth state where they rarely divide. The fundamental problem here is that the vast majority of our pharmaceutical antibiotics are specifically designed to target and kill actively dividing cells.
Ah, I see. So if the bacteria are just hibernating?
The antibiotics just pass them by. They're functionally immune to the treatment because they aren't performing the metabolic actions the drugs are looking to disrupt.
That is terrifying. And we are talking about some heavy-hitter pathogens here, right? Things like MRSA, Pseudomonas aeruginosa, and Enterococcus. What fascinates me, especially given my background, is how these bacteria coordinate to build the structure in the first place. They use a communication method called quorum sensing, right?
That's it, exactly. Quorum sensing is a chemical signaling system. Single bacteria release chemical signals into their environment, kind of like leaving a scent trail. When enough bacteria gather in one place, the concentration of those signals hits a critical threshold.
A quorum.
Exactly. That triggers a collective behavioral change, and suddenly they all start building the EPS matrix together at the exact same time.
You know, sitting here listening to you describe quorum sensing and collective behavior, I instantly recognize that exact mechanism. It mirrors how a bee colony operates perfectly.
Oh, absolutely it does.
A single bee doesn't make major decisions. But through chemical pheromones, the colony collectively senses when the population is too high and it's time to swarm, or when they need to build new wax comb, or when they need to defend the hive from a predator. It is a highly coordinated superorganism.
It's a beautiful system in nature.
It is. But in the case of a chronic wound, that superorganism is the enemy. So if modern antibiotics are failing because of this physical wall, the chemical moat, and the hibernating bacteria, how on earth does Manuka honey break through?
This is where the microbiology gets really exciting. Manuka honey doesn't just have one trick up its sleeve. It deploys a triple mechanism. 3 simultaneous actions that work synergistically to collapse that EPS matrix. And this is vital for you to understand. No single target antibiotic currently on the market can do this.
This is exactly what I wanted to get into. Let's look closely at this triple mechanism, because this is the core of why this specific honey ends up in a hospital instead of on a piece of coast. What is the first mechanism going to work on the fortress?
Mechanism number 1 relies on a compound called MgO, which stands for methylglyoxal. MgO is a tiny, highly reactive molecule naturally present in high concentrations in Manuka honey. And when I say tiny, I mean it has a molecular weight of only 72 Daltons.
Hold on, for the layman listening, what does 72 Daltons actually mean in context?
Great question. A Dalton is just a unit of mass used for molecules. For context, a typical prescription antibiotic molecule might be several hundred or even over 1,000 Daltons in size.
Oh, so they are huge compared to MgO.
They are massive, clunky molecules. Because MgO is only 72 Daltons, it is unbelievably compact. It completely bypasses that first bacterial defense we talked about. It easily slips right through the dense physical barrier of the thick EPS matrix like sand through a chain link fence.
So it sneaks right past the fortress walls without getting stuck. What happens once that MgO is inside the fortress?
It immediately goes to work damaging the bacteria through a chemical process called glycation. MgO irreversibly cross-links with the amino acids in bacterial proteins and the nucleotides in their DNA.
It binds to their DNA.
Yes. It essentially mangles the bacteria's fundamental structural machinery, creating what we call advanced glycation end products, or AGs.
So it isn't just targeting a specific metabolic pathway like an antibiotic does. It is literally scrambling their DNA and structural proteins.
Yes. And because it attacks these broad-spectrum fundamental building blocks of the cell, rather than a specific targeted pathway, the bacteria cannot evolve resistance to it. They cannot mutate or modify their basic structural components to hide from MgO without killing themselves in the process.
That is a massive advantage over traditional antibiotics, where resistance is a constant, terrifying threat. But from my understanding of the commercial side, there is a catch with MGO. It requires a specific concentration threshold to actually do this kind of structural damage, doesn't it?
That is a crucial clinical rule to remember. To successfully disrupt these established biofilms, the MGO concentration in the honey must be above approximately 400 milligrams per kilogram.
400.
Anything less than 400, and you might get some basic surface-level antibacterial action, but you will not break down the biofilm fortress. And of course, the clinical data shows that even higher potencies like 500 or 800 milligrams per kilogram produce even better, faster results.
See, this makes perfect sense from my side of the industry. For anyone listening who wonders about the price tags, this is exactly why certified high MGO reserves are so heavily monitored, strictly graded, and highly valued in the commercial honey supply chain.
It's not just arbitrary grading.
Not at all. It isn't just a pricing tier. The grading directly correlates to whether or not the batch hits that 400 milligram clinical threshold. If it doesn't hit the mark, it doesn't get to do the heavy lifting in a medical setting. So MGO acts like a tiny bomb slipping through the walls. But a bomb isn't enough if the environment inside still supports the bacteria. What else is the honey doing to the wound bed?
That brings us to mechanism 2, which is a relentless acidic attack. Manuka honey has a naturally low pH, typically sitting anywhere from 3.2 to 4.5. To give you some context on that, healthy human tissue has a neutral pH of 7.0.
So it is highly acidic compared to the rest of the human body. How does dropping the pH disrupt the bacteria?
Most bacterial enzymes, including the ones they use to maintain that EPS matrix, are perfectly optimized to function in a neutral environment. When you introduce that acidic pH of 3.2 to 4.5, it completely cripples bacterial enzyme function and disrupts their membrane transport proteins. They simply cannot operate in that acid.
They just shut down.
But here is the truly synergistic part. That acidic environment actually accelerates the MGO glycation we just talked about. The low pH makes the MGO even more reactive and destructive to the bacteria's DNA.
It's like the acidity softens up the target so the MGO can hit it even harder.
Precisely. And there is a massive bonus for the patient here when it comes to the human side of the healing process. In chronic non-healing wounds, the human body gets confused and often overproduces certain protease enzyme called MMPs.
MMP?
Right. These are essentially rogue human enzymes that end up accidentally degrading the body's own newly formed growth factors and fresh collagen. It basically stalls the healing process completely.
So the body's own enzymes are accidentally keeping the wound open and preventing new skin from forming.
Yes, exactly. But the low pH of the medical honey actually stops those destructive MMP enzymes in their tracks. It shuts them down, which protects the new collagen, and essentially restarts the body's natural healing clock.
That is incredible. Okay, so we have MGO scrambling the DNA and the acidic pH crippling bacterial enzymes while simultaneously protecting the patient's new tissue. But we still have this physical scaffold of the EPS matrix sitting in the wound. What is the final piece of the puzzle that clears it out?
The third and final mechanism is osmotic pressure. We have to remember that at its core, honey is a supersaturated sugar solution. This creates massive osmolarity.
As a beekeeper, I actually know exactly how this works mechanically in the hive. But for everyone listening, let's paint a picture of what osmotic pressure actually does inside the wound bed.
Think of it like a powerful vacuum. Because the honey is so dense with complex sugars and so lacking in free water, it desperately wants to absorb moisture from its surroundings. When you apply it to the wound, it creates immense osmotic pressure that sucks water right out of the bacterial cells. It severely dehydrates them.
And what does that sudden severe dehydration do to the fortress itself, the EPS matrix?
It causes the entire structure to collapse. The EPS gel requires a massive amount of hydration to maintain its three-dimensional shape. When the honey sucks the water out, the scaffold dries up, shrinks, and literally falls apart, leaving the bacteria totally exposed to the MGO and the acid.
I absolutely love this mechanism because it mirrors exactly what the bees are doing to create the honey in the first place. When foragers bring in floral nectar, it is mostly water.
But it's very thin.
Yeah, to turn it into raw honey, the hive has to aggressively fan it with their wings, driving off the moisture content until it cures into a super saturated state. They use dehydration to preserve their food source and prevent fermentation. And in the hospital, medical professionals are using that exact same dehydrated state to suck the life right out of the bacteria. It also helps clean the physical wound out, doesn't it?
It does. That osmotic vacuum effect draws out wound exudate, which is the medical term for the fluid pooling in the wound. This significantly reduces painful swelling for the patient and promotes something called autolytic debridement.
Autolytic debridement.
That is just a medical term for the body using its own natural moisture and enzymes, pulled to the surface by the honey, to flush out and clean away dead tissue. It physically removes the organic debris that the biofilm was anchoring itself to.
So it destroys the walls through dehydration, scrambles the invaders with MgO, cripples their defenses with acid, and then flushes the debris out of the wound. That triple mechanism is a brilliant evolutionary design. But I want to play devil's advocate for a second. Let's look at the alternatives. Because doctors use silver dressings in burn wards and for chronic wounds all the time. People swear by silver. Are you saying silver doesn't work against these infections? How does medical-grade Manuka actually stack up against standard treatments?
It's not that silver doesn't work at all, but your skepticism is well-founded when we're talking specifically about biofilms. Silver dressings absolutely disrupt bacterial cell membranes of free-floating bacteria. But when you look at the clinical data on established biofilms, silver only has moderate EPS penetration.
It can't punch through the wall.
It really struggles to get all the way through those thick fortress walls. And because it gets slowed down, there is a moderate risk of the bacteria surviving long enough to develop resistance to it. It is a good tool, but it is not bulletproof against a fortified hibernating colony. Manuka is the only agent that deploys a triple simultaneous mechanism.
What about traditional topical antibiotics, the prescription ointments doctors write every single day?
They fare even worse against biofilms. Topical antibiotics have incredibly low EPS penetration. Their molecules are just too large. They literally bounce off the physical barrier or get chewed up by the chemical moat of beta-lactamase we talked about earlier. Consequently, they carry a very high resistance risk. An antibiotic is a single target mechanism, which makes it incredibly easy for the bacteria to figure out a workaround or just wait it out in metabolic dormancy.
Which brings us back to why the medical community is paying so much attention to this. I know you spend a lot of time reviewing the clinical evidence on wound microbiology. Without getting bogged down in reading off author names, publication years, or academic jargon, what is the actual clinical proof that this triple mechanism is working in real patients?
The clinical proof is frankly staggering. Multiple peer-reviewed studies have shown that when you use high MgO honey, specifically those hitting that 400 milligram threshold we talked about, you see a greater than 90% reduction in MRSA biofilm mass within just 24 to 48 hours.
A 90% reduction of MRSA, one of the most notoriously antibiotic-resistant pathogens on Earth, in just 2 days. That is huge.
It really is. Yeah. Another landmark study found that medical honey causes the total disruption of the alginate EPS matrix. Alginate is basically a highly specific gooey armor produced by Pseudomonas aeruginosa, which is one of the most stubborn, persistent pathogens we face in chronic wounds. The honey completely dismantled that armor.
That's amazing.
And if you zoom out to look at the big picture, a major independent systematic review, a Cochrane review, which is widely considered the gold standard for evaluating medical evidence, found that using medical-grade honey protocols leads to significantly accelerated healing rates in confirmed biofilm wounds compared to standard antibacterial dressings.
And I think it is important for you listening right now to realize that this isn't just theory, and it certainly isn't alternative medicine or a home remedy. If you look at the research page, there are actual FDA-cleared medical honey products sitting in pharmacies and hospitals right now. And the site literally lists their 510K clearance numbers, which links straight back to the official FDA database.
Yes, exactly. This is fully integrated into modern regulatory frameworks. Medihoney, for example, was the very first FDA-cleared medical-grade honey product. There are several others out there now, like TheraHoney in the U.S., and products like Activon and Surgihoney Euro that are CE marked over in Europe. They have to pass rigorous medical standards for absolute sterility and consistent MgO potency before they ever touch a patient.
It just proves that the scientific community isn't treating this like a folk remedy. In fact, if you scroll down on the site we mentioned earlier, there's a section called Latest Biofilm Research that has a live feed directly from the NCBI PubMed database.
I love that feature on the site. It proves how dynamic this field of study is. Researchers are actively publishing new breakthroughs on honey and wound care right now. It is a constantly evolving science, and that live feed shows you exactly what the scientific community is discovering today, this month, this year.
So the next time someone asks me why Manuka is worth what it costs, I have a pretty clear answer. It is not just honey. It is a triple threat weapon against infections that antibiotics can't touch.
It truly is. And it makes you wonder if bacteria simply cannot build resistance to MgO because it attacks their fundamental building blocks. Could this natural triple threat mechanism become the actual blueprint for an entirely new resistance-proof class of synthetic drugs in the future? We are currently facing a global crisis of antibiotic resistance, and the answer to outsmarting these pathogens might be hiding in plain sight, perfectly engineered by nature.
That is an incredible thought to end on. As a reminder, if you want to see exactly how this works for yourself, we highly encourage you to visit manukawoundscience.org. You can read the full biofilm destruction page, explore all the clinical references that have been verified through PubMed, and check out that live research feed we just talked about.
It's an incredible resource if you are as fascinated by this intersection of nature and modern medicine as we are.
Thank you so much for joining us as we explore this amazing topic. We hope you learned something entirely new today.
Take care, everyone. Keep asking questions and keep exploring.